Okay. Hello, everyone. So today is the last session of our SNARGs study group, and we'll be talking about, again, constructing arguments, but from another object called IOP, Interactive Oracle Proofs. This whole book, you can think of it as constructing arguments from different types of objects. And as you have seen in previous weeks from my lab mates, we have many of these transformations. And in the beginning of the study group, you've probably seen how to start from an IP, an interactive proofs, and the Fiat-Shamir transform from IP takes an IP and it converts it into a non-interactive argument. And if we start from some other objects, say the PCP, and along with Merkle commitment, we have the Killian transform, which takes PCP, a probabilistic checkable proof, and Merkle commitment, and you get an interactive argument. And building on top of Killian, we've also seen the Micali transformation, which takes PCP and a Merkle tree commitment. And the Micali transform will turn that into a non-interactive argument. So these are transformations that starts from PCPs. We didn't really talk about this because the soundness proof in the book of Micali is a direct proof. But actually, you could think of Micali as being first as a modular version of Micali, as first doing Killian, and then perform Fiat-Shamir on the interactive argument, which takes interactive argument and make it into a non-interactive one. Then this is a bit subtle here because the Fiat-Shamir transform, as I said, just here is like taking an IP and turning it into a non-interactive argument. But the result of Killian is an interactive argument. But it turns out that in this case, Fiat-Shamir on IP, when it's acting on an interactive argument, the soundness can still be bounded. So like it can also work when, in this case, taking an interactive argument and transform it into a non-interactive argument. We will see this later in the proof of today's talk. And yeah, it's a little bit of subtlety here. So today we will be looking at two new transformations, two new constructions known as the IBCS and BCS construction. So instead of starting from PCPs, we'll be starting from interactive oracle proofs. So it's generalizing PCPs into multiple rounds. We will have randomness and interaction in the interactive oracle proofs. And from IOP, along with the Merkle commitment, we'll look at the interactive BCS, so IBCS construction, which will give you an interactive argument. The IBCS construction is an IOP analog of the Killian construction. And then building on top of that, we'll look at the BCS construction, which takes IOP and Merkle commitment and turn it into an argument. So that is the IOP analog of the Micali construction. And again, you can think of BCS as first doing IBCS and then doing Fiat-Shamir on the interactive argument. Oh, sorry, this should be non-interactive. Oh, and also, if you have any questions, feel free to interrupt anytime. Yeah, so here's like basically an outline. The way I'm going to approach this is I will first try to give some high-level definitions and definitions. Then for the proof part, I'll just try to go through it like on a high level so you can maybe read the details on your own much more easily. So today we'll be focusing on these two constructions. We'll first start with some definition of IOP, and then we'll talk about, as well as the state restoration soundness of IOP. It's very similar to state restoration soundness of IP. And then we'll talk about IBCS construction. And then the third section is on BCS construction. I will mainly focus on the first three. To start, what is an interactive oracle proof, IOPs? We've seen from IP, it's very similar. We also have a prover and a verifier. The prover takes as inputs the instance and a witness, and the verifier takes as input just the instance. Recall that in IP, you would have the prover sending message alpha1, the verifier sending message row1, and then the prover sent another message, and the verifier sent another randomness dot, and then in the end, you have k rounds. And the verifier would read all of these messages, alpha1, alpha2, alpha k, in its entirety. And in the end, it outputs a decision bit B of whether accepting or rejecting.
Quick question. I noticed your last PK arrow is in a different direction than all the other P arrows.
Oh, I'm so sorry. Yes, you're right. You're right. It's also sent by the verifier to the prover. Yeah, so it's basically an IP of K rounds. And now for interactive oracle proof, the only difference is that now instead of for the prover sending these messages, we'll have the prover sending PCP proofs or proofs that the verifier can then query at certain locations. This is, in a sense, very similar to PCP if you just look at one round of an IOP. But here, the prover sends some proof pi1, and the IOP verifier will query the pi1 at certain locations and send some randomness row1. Then the IOP prover sends another proof, and the verifier query it at some other location depending on its randomness, and sends another randomness, and you continue for k rounds. And then in the end, the verifier, it outputs a decision bit. Its decision bit is dependent on the instance X, on its randomness row, and also it has oracle access to all of the proofs sent by the prover. So it's also dependent on the query bits. So the query answers that is solved from all of the IOP proof strings. And it outputs either accept or reject based on these things. Here we also, similar to the notion of public key IP, we also have the definition of public key IOPs. What public key means is that all of these row i's, they are uniform randomly chosen. They are just random strings that are drawn from of some predetermined length. And other than these row i's, the verifiers do not have any additional randomness itself. So the randomness of the verifier, so this row here, is exactly the row i's that are sent to the prover across the k rounds. Then you can write the verifier accepting the verifier decision bit as a function of just X and the row i's. And it's able to query all of the IOP proof strings depending on the location is depending on its randomness. And without loss of generality, when it is public key IOPs, we can also think of the IOP model as having two phases, an interaction phase and a query phase. So instead of thinking the prover sends some proof, the verifier query, and then send randomness, and then the prover sends another proof, the verifier querying it, and then send randomness, you can just separate out the interaction and the querying part. So say now the provers just send the proofs, the verifier just sent row 1, and then the prover sent pi2, the verifier just sent row 2, dot, and the prover sent pi3, and the verifier sends row k. This is pi k, and this is the interaction phase. And after this point, the verifier have access to all of the IOP proof strings and its randomness. Then it can just query all of the pi i's that it already possesses. Yes, so that's a note on public key IOP, which is what all of the constructions that we will now only work with public key IOPs. So the IBCS and BCS protocol are built using public key IOP. Very similar to all of the proof systems that you've seen before, we can still define completeness and soundness in a similar way. So then an IOP for a relation R has perfect completeness if for every instance and witness pair in the relation, and the interaction between the prover and verifier should always accept. This bracket notation is basically is a random variable that equals the output of the verifier after interacting with the prover. The probability is taken over randomness of the provers and the verifier. Yeah, it's just a notation to denote interaction. It's basically the same as how we did it in the IP case. And we say that the IOP has soundness error epsilon IOP if for every instance not in a language and malicious IOP prover, the probability that this interaction ends up in accepting is less than equal to the soundness error. So this is defined for every instance X. You can additionally define, this will be used in the non-improving adaptive soundness. So adaptive soundness bound is using this notion is epsilon IOP n. So it's saying it's the maximum soundness error of any instance of size less than equal to n and not in the language.
The distinction there was like soundness over all instance strings versus over those of a certain length.
This one? So this one is, so this one is the soundness that we will use when we talk about non-adaptive soundness because it's specific to an instance. If we look at, we'll see later, and I'll also mention it when talking about the adaptive and non-adaptive soundness. But in the non-adaptive soundness, since the prover is picking the instance, then we need to say the prover can pick any instance of length less than equal to n. So you just bound the soundness by this one, which is the maximum soundness error for any instance less than equal to n.
I was a little okay. So if the prover is picking the instance, then yeah, I think I just got a little lost here. That's okay. You can go on.
So the soundness, so it's the malicious prover who would be picking the instance.
That's right. Sorry. So my confusion was like, I thought adaptive soundness is when the malicious actor is allowed to make the choice, or is it the other way around? Like,
Right.
I'm surprised you're calling this non-adaptive. This seems to me like it would be adaptive because the malicious actor is adaptive.
Yeah, that's a great question. I might have had a mouth slip. So yeah, exactly as you said, adaptive means is the malicious prover is able to choose the instance. So it can choose
This
any
should have been
instance of length less than equal to n. That's called adaptive soundness. And non-adaptive soundness is proven for every instance x. You can bound the soundness of argument is less than or equal to the soundness of maybe IOP plus Merkle tree extraction error. So you say that for any instance x not in the language R. Does that answer your question?
Yeah, and I just want to make sure that the conclusion was correct. Like, this case is adaptive.
Right. So this notion here that talks about the maximum over all instances of length less than or equal to n is for adaptive. Okay, so another interesting thing to note here is that we think about IOP as a more generalized version of IP and like more general notion than IP. Then instead of just having the prover sending proofs pi i's here, we can also have the prover send along with pi some like non-oracle messages, alpha 1, alpha 2, and alpha k. Then these alpha i's are read in its entirety by the IOP verifier, whereas the pi i's, they're only read at the maybe constant many query locations. Then in this model, it's more generalized general definition of IOP. The verifier, its decision bit becomes this. So it'll be dependent on the instance and also all of the alpha i's that are non-oracle messages and all of the query randomness, all of the verifier randomness. And depending on its randomness, it'll query the pi i's at certain locations. And then based on this, it outputs some decision bit. So all of the construction that we'll see later today, like IBCS and BCS, they will also work for this type of IOP. You would need to modify the proof a little bit, but if you do that, there will not even be overhead if we look at this more general definition. Yeah, so here it's basically the book talks about these things in a little bit more detail. You can look at it on your own. So like public coin IOP, and similar to all of the proof system definition before, you have lots of different parameters that you can also look at it offline. And here it talks about the non-oracle messages. And like very similar, you can also define soundness notions, other soundness notions like knowledge soundness, both for the straight line and the rewinding version. Yeah, and also zero knowledge. But yeah, I think we'll move on to, this definition will be useful. So let's see. We talk about this verification on local view. It is also like pretty much the same as in the in PCP. There's also a similar definition. So basically what happens here is that even though the verifier is sending entire proofs, is sending long proofs pi i's, the whole proof pi I is irrelevant to the verifier decision bits, other than the number of bits in pi I, the little amount of the very few number of bits in pi i's that are actually queried by the verifier. So we can replace there was so previously here we had pi I in k, but we can replace that notion with, replace that part with QI, the queries QIs, query sets QIs, and the query answer AIs. And this decision function, what it does is it derives the verifier query location, the query sets, based on the verifier randomness. And if any of the queries fall outside of the query site QI, then the verifier immediately rejects. If it doesn't, then you answer the queries with AI. Yeah, we will see how this is relevant in the proofs later. Yeah, so this is analog to how in PCP, we also had the definition of this kind of decision fit function. And yeah. So in the next section, it talks about IOP state restoration. We have seen in this book, there was PCP state restoration, and there was IP state restoration. And IOP state restoration is very similar to the IP case. The only difference here is that now all of the IP prover messages alpha I are now replaced by the IOP proof strings pi I, and the IP acceptance condition is replaced by the IOP acceptance condition. So nothing surprising here. But yeah, let's just look at the state restoration game again, just to recall. So in the IOP state restoration game, you run the IOP state restoration prover. The intuition behind state restoration games are the fact that the state restoration prover, they are much more powerful than the standard IOP prover, in the sense that they can query the oracles in ith round multiple times before they output some guess of an accepting transcript. They can make multiple queries. And first, the state restoration game runs the state restoration prover, and until the state restoration prover decides to exit the loop. And here, for a T-move state restoration prover, this happens T times. So it makes query of the form of this form. So it's querying with some IOP strings and some salt strings. And notice that the state restoration IOP prover, since we're talking about a K-round protocol, it can query any of the random oracle, any of the K random oracles. It doesn't have to go first query the randomness in the first round and the second round. It can query any of the K, and it can query some more and some less. It doesn't matter. We don't care. And then after the IOP state restoration prover decides to exit the loop, it outputs its final guess of an accepting transcript. And then we set the verifier randomness to the rand I of the ith round randomness set is set to rand I of the hash of those things. Then we output the pi and the IOP proof string, the salt, and the verifier randomness. So even though this is not written in the book, you can do it as an exercise to just sanity check that this state restoration IP soundness, it should also probably be upper bounded by the state restoration of, the IOP soundness with T plus K choose K times the IOP soundness. The reason is very much similar for why we had a similar upper bound for state restoration IP soundness. It's because here, the state restoration prover, when it outputs its final guess of accepting transcript, it could output something from the T queries that it made before, but it could also just guess something that was never queried. This is equivalent to K queries. Basically, across is T plus K queries. As long as K of them forms an accepting transcript, then it's succeeding. Oh, I'm just speaking very high level and intuitive. That's an intuitive reason, but you can look at in the IOP session, the proof should be very much similar. The IOP prover, the state restoration IOP prover wins this state restoration game with much more advantage than the standard IOP prover because it's able to guess more times, and the choices that it has is exactly T plus K choose K. Yeah, and the rest of this part is about how you can similarly define knowledge soundness for also state restoration. And yeah, now we are ready to look at the IBCS transformation, which takes an IOP and Merkle commitment and transforms it into an interactive argument. I will not go through the verbal version of this. You can read it offline, but I think looking at this picture is really helpful. So as I mentioned, this is like the IOP analog of Kilian. So let's see side by side. Let's recall what the Kilian protocol was doing. So Kilian protocol, it takes PCP, Merkle commitment, and gives you an interactive argument. The way that it does that is the PCP prover, it first outputs some proof string. And instead of sending the entire proof string to the argument verifier, the argument prover will first commit this proof string through some Merkle commitment scheme. And it only sends the short commitment, the Merkle tree root. The argument verifier then samples PCP randomness and sends it back to the PCP to the argument prover. It then checks whether the PCP verifier would accept by querying the proof based on query sets based on this verifier randomness. And it then sends back. Oh, sorry. Oh, sorry. I missed. Oh, sorry. That was not the argument prover. Based on this verifier randomness, it induces a query set Q, PCP answers A, and a Merkle tree proof for that opening. And it sends over these things to the argument verifier. And the verifier checks that the Merkle tree indeed accepts, the Merkle tree check passes, and that the PCP verifier would accept. If you zoom in on the IBCS transformation, it is just like the first part here. It is exactly the same as the Kilian construction. The only difference here is that we're starting from an IOP, which has K rounds. So after pi 1, we have pi 2. The IOP prover will produce pi 2. And then we just repeat the same thing again. We just commit to pi 2 and send over the root. And the argument verifier sends back its IOP randomness. And we repeat for K rounds. In the end, the IOP verifier, the argument prover will send over the IOP queries and oracle answers for each of these K rounds, and also the Merkle tree proof for all of the K rounds. And then the argument verifier checks that all of the Merkle tree check passes and that the IOP verifier accepts. The only thing that's a bit different is, so we need to note that the Merkle tree scheme here it could be using Merkle tree commitment scheme of using different parameters, because in the IOP, the different pi i's, they may be of different length. So say pi I is of length Li, then we should be using a different Merkle tree commitment scheme. So it should be is a different configuration of the Merkle tree commitment scheme. So Merkle tree I is Merkle tree commitment scheme on message of length Li. And then we can bound non-adaptive soundness of this IBCS construction. It says that the soundness of the argument is upper bounded by the IOP soundness and the Merkle tree multi-extraction error. This Merkle tree multi-extraction error is slightly different from the ones that we've seen before. So recall that in Mikali, the Merkle tree extraction error is this one here. It's basically saying whether the adversary can find it can output some commitment and opening and proofs that passes the Merkle tree check, but it cannot be extracted correctly. So it's the multi-extraction error across multiple extraction. Here, as I mentioned before, because we're using different configurations across different rounds, we have another multi-extraction error where we allow the MTIs to be different configurations. And the Merkle tree multi-extraction error that we were using before in Mikali is a special case of this Merkle tree extraction error that we are using now. Yeah, and intuitively, it makes sense that the argument soundness is bounded by the IOP soundness and Merkle tree extraction error. It's because it's very similar to all of the transformation we've seen before, Killian and Mikali. More specifically, the proof is construct. So it says it's proved by proving this lemma. So it says for every T query argument prover P tilde, there exists an IOP prover such that the argument soundness is bounded by IOP soundness plus Merkle tree extraction error. And the IOP prover is defined here. It essentially runs the argument prover and extracts the IOP proof and use those IOP proof to interact with the IOP verifier. In the proof, we start with the argument soundness, and this is just by definition of argument soundness. The argument prover is run. In every round, it outputs root I, it receives randomness row I, and in the end, it outputs some Merkle tree proof of the queries and answers. And then the argument verifier checks if the IOP verifier accepts and all of the Merkle tree check passes. Then this probability, by total probability, we conditioned on, this is is actually equal to when this probability is conditioned on all extraction succeeds and conditioned on at least one extraction fails. You can bound the first probability, so when all of the extraction succeeds, oops. Oh, interesting. So when all of the extraction succeeds, you can replace these QIAIs with actually just pi i's, as we have seen before, because the extraction exactly tells you at location QI's of pi I, the query answer is AI. So you can just let the verifier use those IOP proof strings instead. And we can also throw away this condition, and it's still going to be an upper bound. And that will give you the IOP soundness. And then this term here, it's exactly, if you look at it long enough, it turns out to be the Merkle tree multi-extraction error when you can have different configurations. The adaptness soundness is proved almost the exact same way, whereas now we're using the IOP soundness with this instance, and which we've seen before. So it's the maximum IOP soundness across all instances of length less than or equal to n. So I've highlighted all of the difference in the adaptive soundness proof. So here the argument prover can pick any instance that's of length less than or equal to n and not in the language of this relation. But the proof still mainly follows similarly. Except here you need to discuss the first round and then the later round separately. So because the output of the argument prover will look slightly of different form. So when I equals 1, the argument prover outputs the instance X and the Merkle commitment. So it outputs X and the Merkle commitment. And in later rounds, it just outputs Merkle commitments. But yes, you can try to follow this proof and appreciate how the change it follows from non-adaptive soundness to adaptive soundness. Yeah, and now let's finally come to the main topic of today, which is the BCS transformation. The BCS transformation, B stands for Van Sassen, Chiesa, and Spooner. It came out in 2016. And as I mentioned before, it's the IOP analog of the Mikali transformation. So you're taking a public keying IOP and a Merkle tree commitment. And through the BCS transformation, you get an argument. And let's see. So I have the Mikali construction on the left. And this is the BCS construction. Just to recall how the Mikali construction works. So before in Kilian, we were sending the Merkle tree commitment root to the argument verifier and then receive back the PCP randomness. But here, to turn it non-interactive, we are using another random oracle FS so it produces its own PCP randomness using the instance, the root, and some random salt tau. It is important to hash the root here because in the interactive argument, it's sending the Merkle commitment and then the verifier sends the PCP randomness row. Hashing the root is saying it's forcing the argument prover to first pick the commitment, to first commit to something and then pick the randomness. It cannot first look at the randomness before it has committed. That's why this is important to include as an input to FS. Our is set, a query answer, Merkle tree proof, opening proof, and the salt. It then derives its own PCP randomness using FS. It derives the PCP randomness by itself, and then it checks that the Merkle tree check passes and that the PCP verifier accepts. If you also zoom in closer here, it is the exact same in the BCS transformation if you just look at one round. So if I just zoom in here, that looks the exact same as in Mikali transformation. But then exactly that's the exact why this is an IOP analog, is that now we need to do this for K rounds. So after getting the first randomness row 1 for round 1, we are gonna include row 1 in the next hash and hash it, use F2, query F2 with row 1, the second Merkle commitment. So like we commit the second IOP proof string to root 2, and then query F2 with the verify randomness from the first round, the second Merkle commitment, and a new salt, random salt. And this gives us row 2. And we continue this process. So actually, this is basically using the faster variant of Fiat-Shamir protocol on IBCS. So what I mean is here, in the faster variant of Fiat-Shamir, we're also hashing the row i's in as part of the query to F2. In the normal Fiat-Shamir, what we're doing is instead we'll be querying F2 with alpha 1, alpha 2, and tau 1, tau 2. Then you query alpha 3 with alpha 1, alpha 2. Like you query the random oracle in the ith round with all of the previous prover messages and salts. But then the query size, the input size grows as the round continues. But in the faster variant, what we're going to do is we take out alpha 1 and row 1 and replace that with row 1, tau 1. And we take out alpha 1 and tau 1 and replace that with the hash of them, so row 1. And there was a procedure of how you can, so basically you're constructing a hash chain this way in the faster variant, and you can recover the original query in like the standard Fiat-Shamir through this kind of hash chain. The caveat here is that through using this faster variant of Fiat-Shamir, you get an additional error term here in the soundness bound for the argument. So if we were to use the standard Fiat-Shamir transform, then you can also avoid the soundness error. But since we are using the faster variant, it also gives rise to a small loss in the soundness upper bound. Yes, so in the BCS construction, the argument prover continues doing this kind of hash chain and committing each of its IOP proof strings for all of the K rounds. And in the end, what it's sending to the argument verifier contains all of the Merkle tree commitments, the query sets, the query answers, Merkle tree opening proof, and the salt for each of the K rounds. Given this argument proof, the argument verifier can derive the IOP randomness itself using this kind of hash chain, exactly like how the honest argument prover derived the verifier randomness. Then in its decision bit does 2-check. It checks that the Merkle tree proof, the Merkle tree check passes, all passes, and then the IOP verifier accepts. So we can bound the soundness of the argument as a result of the BCS transformation by the state restoration, IOP state restoration soundness, the Merkle tree multi-extraction soundness with different configuration, plus a small error turn that arises from the faster variant of Fiat-Shamir transformation. And if the parameters satisfy some bounds, the multi-extraction error can be absorbed into this small error term, and you end up with the state restoration error plus some term of order of this small error. There are two approaches presented in this book on how you can prove theorem 25.2.1. The first one is the direct approach. It is also the approach that's how we proved Mikali soundness. You directly define the state restoration IOP prover and upper bound the argument soundness by having the state restoration prover play the state restoration game and winning the state restoration game. So it means that the state restoration game should output some tuples so that would make the IOP verifier accepts. And it's gonna be upper bounded by the state restoration IOP error, and plus the Merkle tree multi-extraction error and the small error. The construction is very similar to how we constructed the state restoration prover, the PCP state restoration prover in the Mikali construction. The difference is that here, instead of the argument prover can query any of the FIs, whereas in Mikali, it has to be it can only be querying FS. So here it can query the random oracle for any of the K rounds. And if it's querying the first round, then the query should look something like this. Otherwise, it will look something like this. So you discuss both cases and have the state restoration IOP prover perform the Merkle tree extraction, and then query the IOP state restoration game using the IOP proof string instead. Yeah, so the queries that it receives is of the form bunch of Merkle tree commitments, since it's running the argument prover, but it will extract from those commitments, and using the Merkle tree trace to extract, it will extract out the IOP proof string and query the IOP state restoration game with those proof strings instead. And the final proof is by proving this. The theorem is proved by proving this claim, is saying that these two distribution are their statistical distance is bounded by the Merkle tree multi-extraction error and the Fisher-Shamir faster variant loss. Another proof approach is to use a more modular approach. So as I mentioned before, the BCS transformation can be seen as doing the IBCS transformation on IOP and the Merkle tree commitment. You get an interactive argument, and then you perform Fisher-Shamir, the faster variant, to get a non-interactive argument. In this modular approach, we can first prove a lemma. Here, it upper bounds the state restoration IOP soundness. State restoration IP soundness of the interactive arguments that were the result of the IBCS, and it bounds the state restoration IP soundness by the IOP state restoration soundness and the Merkle tree multi-extraction error. It's then, after that, you can, so basically the conclusion of that claim is that the state restoration IP soundness is bounded by state restoration IOP soundness, and the Merkle tree multi-extraction. And then you can and then we perform Fiat-Shamir, so we bound the argument soundness by the state restoration IP soundness plus the error term of the faster variant of Fiat-Shamir. The subtlety here is that since Fiat-Shamir is actually defined for IP, but here in the interactive argument constructed from IBCS, the prover also uses a random oracle FMT. So it's also making Merkle tree queries. But the way that it still works nicely is that since when we are proving Fiat-Shamir soundness, the Fiat-Shamir protocol itself, it does not use any commitment scheme. So it's only making black box use of this argument prover. And even though this argument prover is making additional queries to FMT, if we just let the state restoration IP prover to forward the argument prover's queries to FMT and just still responds to its FMT queries as it would have received, then it doesn't change the behavior of the argument. So here we use this notation to refer to augmenting the usual IP state restoration prover of Fiat-Shamir, and it's augmented to forward queries from the argument prover to FMT and return the corresponding answer. And you can still prove state restoration the Fiat-Shamir soundness similarly. So it'll still give rise to this small error term. And yeah, so here's a summary. What this shows is that the argument soundness is bounded by state restoration IP soundness and a small error term. So that's this part of the transformation. And then, so that's the first half. And then we can further bound the state restoration IP soundness by state restoration IOP soundness plus the Merkle tree multi-extraction error. And that's basically the first part of the transformation. Yeah, and that would conclude soundness upper bound for BCS. Yeah, are there any questions? Okay. Good. Thank you all for coming. I hope you enjoy the study group, and yeah, this area of research is very rich, and yeah, it is definitely very technical. Yeah, it takes a lot of going back and forth to see the connections, but I hope you enjoyed, and yeah, thank you.
Yeah, thank you so much.